When electromagnetic waves of a high enough frequency hit the surface of a metal, the metal will emit electrons. For most metals, this frequency falls in the UV range. This is called the photoelectric effect. A simple way of observing such a phenomenon is to use a gold leaf electroscope. This is a box containing a thin gold leaf attached to a metal rod. The rod holds a zinc plate and is insulated at the top, preventing the charge escaping the plate. The leaf is initially repelled away by negative charge. Now, what happens if you shine red laser light onto the zinc plate? Well, even if the intensity is very, very high, nothing happens. However, if you shine a small amount of ultraviolet light onto the zinc, the leaf will slowly fall down, even at really low intensities. Three main conclusions can be drawn from this. Firstly, no photoelectrons are emitted if the radiation's frequency is below a certain threshold. Secondly, the photoelectrons are emitted with a variety of kinetic energies. And finally, the number of photoelectrons emitted per second is proportional to the intensity of the radiation. As remarkable as this discovery was, it couldn't be explained by scientists. According to wave theory, energy from the light would be spread evenly over the wavefront, and each free electron on the surface would gain a bit of energy from each incoming wave until they had enough to escape. There's no explanation for the kinetic energy depending only on the frequency. Or is there? In 1905, Albert Einstein published a paper on the hypothesis that light energy exists in discrete packets called photons. The energy carried by one photon is equal to hf, where h is Planck's constant and f is the frequency of the light. Einstein saw these photons of light as having a one-on-one particle-like interaction with surface electrons. He suggested for the first time that light is both a wave and a particle. This is called the wave-particle duality of light and was so influential Einstein won a Nobel Prize in Physics for it in 1921. The photon model states that when light hits the metal surface, it's bombarded by photons. If one of these photons collides with a free electron, the electron will gain energy equal to hf. But before it can escape the surface, it needs enough energy to break the bonds holding it there. This energy is called the work function and has the symbol phi. If the energy gained by an electron exceeds the work function, the electron can escape. If not, the photon isn't absorbed and will most likely pass straight through. Electrons lose energy in doing work to escape the metal, with electrons deeper down losing more energy than those on the surface, leading to a range of different energies. This is all neatly tied up in Einstein's photoelectric equation. He said that the energy of the photon was equal to the work function plus the maximum kinetic energy of the photoelectrons. This means the kinetic energy of the electrons is independent of the intensity, as they can only absorb one photon at a time. The photoelectric effect plays an enormous role in everyday life. Solar panels, for example, are nothing more than a series of metallic plates that face the sun and exploit the photoelectric effect. The light from the sun will liberate electrons, which can be used to power gadgets, run your lights, or in sufficient enough quantities, power everything in your home.